Hello everyone, my name is Robert Crowley. I'm a PhD student in the UCR Department of Chemistry, working under Dr. Kevin Coe, and today I'm going to talk to you briefly about our work our lab is doing into the field of chemical catalysis, new processes that allow access to key molecules. Before I get too dug into the nitty-gritty though, let's talk briefly about what chemical catalysis is and why it's important. Starting with why it's important, chemical catalysis is used in a wide array of reactions used to synthesize molecules that are often found in a number of consumer products. So, for example, pharmaceuticals, fragrances such as perfumes, as well as dyes. Most, if not all, of these molecules require one or multiple chemical catalytic steps in order to synthesize so that they can be used in the products that they are needed for. But how exactly do the catalysts work? In order to understand that, you need to have a base understanding of how chemical reactions work. Generally speaking, you take some starting material, A and B, and you combine them together, usually forming new bonds, to generate a molecule AB. This requires the passage of a certain energetic barrier, and in some cases, at room temperature, that barrier can be surpassed. However, in other times, the barrier becomes much too high, and as a result, the reaction can't proceed without the need of external help. But what exactly do I mean when I say external help? Well, to understand that, let's take this idea of chemical reaction and bring it to something that's a little bit more mundane. Let's say climbing up a hill. In its general form, it can be relatively easy to climb up some hills. They're relatively short, not particularly steep, and once you've gotten to the top, it's very easy to get down to the bottom of the hill and get to where you're going. However, sometimes the hill can be far too steep or too tall, and as a result, you're not able to get to the top without some kind of external help. Let's say perhaps like a bike. Using a bicycle, you can get to the top of the hill significantly more quickly and access hills that you might not normally be able to do with your own 2 feet. However, as anyone who's ever ridden a bike up the hill would know, sometimes even that isn't enough, and you need some kind of motorized vehicle to get to the top. Let's say a car. These two groupings, or these two types of vehicles, can sort of be used to represent the types of catalysts that we use in a chemistry setting. So let's start, in this case, with bikes. So in this case, a bike would usually be used to represent some kind of iron, copper, or nickel-based catalyst, with the positives being that they're usually significantly less expensive and easier to work with than the car-type catalysts are. They do have the negatives that they can't access anywhere near as many products, and individual catalysts themselves are significantly less multi-purpose, only allowing access to 1 or 2 specific reactions without the need of significant modification of the actual catalytic system. Alternatively, cars, in this case representing palladium, rhodium, or iridium-based catalysts, are capable of a lot more reactions, and oftentimes individual catalysts themselves are more multi-purpose. However, they're much more expensive, largely owing to their low earth abundance, meaning that we will inevitably run out of them over time. Oftentimes, these reactions are also more air sensitive, requiring a much more careful conditions to be met in order for them to work properly. The chemistry that we are developing in our lab fits nicely into these two categories, and let's start talking briefly with our work into new, fancier cars. So, recently we reported the use of rhodium to generate new carbon-carbon bonds. And this reaction is particularly interesting as it may allow access to a molecule known as berberine, a molecule that's found in a number of traditional herbal medicines and has been directly linked to their medicinal properties. We hope to use the chemistry that we've recently developed to synthesize the rings marked in red, which would normally be significantly more difficult to synthesize using what known means. In the realm of generating bikes that work like cars, we've generated new iron-based catalysts to form carbon-carbon bonds, in this case using iron chloride, a significantly cheaper iron catalyst. We hope to use this process to synthesize adapalene, a known anti-acne medication. both of these are work that's currently still being undergone in our lab. Here are all the relevant references, and I'd like to thank our sponsors for this opportunity.